Hello, everyone, and welcome to Earthquakes. As I was updating this PowerPoint on October the 19th, 2020, there was a remarkable earthquake, or a series of earthquakes, up off the coast of the Aleutian Islands in Alaska. And so, if you're in the geology class that was going on then, you know I delayed this lecture for a couple of days while I got it updated with respect to that earthquake. You're looking at the Iris earthquake browser here, and I'll put there's a link to it in my courses. I'll put it there when I'm done. By the time you see this, it'll be there. It's a really powerful tool for looking at earthquakes. It's a little bit clunky. It's a website. It's a little clunky, but it works. It works well. And so let me slide on up here to the Aleutian Islands, and you can see, first of all, there's a bunch of earthquakes here. I've got it set to show the most recent 4,500 earthquakes. And so you can see that Alaska and the Aleutians is a very earthquake-prone area. Remember, it's a convergent plate boundary, so you're going to get a lot of earthquakes here. Let's narrow that number down to about 1,000. And let's apply that. And now we have fewer, still a lot though, and so let's switch the time range up here. So let's go from now, but let's go ahead and just show. We don't need January of 1970, do we? Let's see. So let me do this, and hold on here. So like I said, it's a little clunky. And so there we go. And so let's just look at the last few days worth of earthquakes here. And if we do that, we see a bit clearer picture, and we can see a very distinctive swarm of earthquakes happening right here off of the Aleutian Islands. And there was a magnitude 7.6, and we'll talk about what exactly that means. There was a magnitude 7.6, followed by, as you can see, a whole bunch of aftershocks. And we will come back and look at this because there's some interesting things going on here. The IRIS data right now have there being 2 earthquakes at the same time, a 7.4 and a 7.6. That is not true. There was only 1 earthquake. So the data will get cleaned up eventually. This is not unusual when you get big earthquakes. You get reports from different seismic stations and different agencies, and you think there were 2, and there was only 1. So it's this one right here, this 7.6. So anyway, so let's take a look at earthquakes and see if we can learn a little bit more about how they work and what's going on. Okay, so here we are in the PowerPoint, and let's learn some stuff about earthquakes. Okay, so earthquakes are among our worst natural disasters, really, because they strike without warning, and they can be very destructive. We can talk about places that are more or less prone to earthquakes. But if anyone tells you they can predict when an earthquake is going to happen, they're telling you something. There are some sort of predictive systems, but not really. And so what are earthquakes? Well, earthquakes, are what happens when you have portions of the Earth's crust sliding along against itself, right? Sorry, needed some water. And so there's 2 words for where the earthquake happened. The one you are probably most used to hearing is epicenter. Now, be aware, though, that the Greek prefix epi means on top of. The earthquake, the epicenter, rather, isn't actually where the earthquake happened. The epicenter is that point on the Earth above where the earthquake happened at a point called the hypocenter or focus. Generally, this hypocenter needs to be at least a mile down. Just because up in here, less than that, you just cannot generate the pressure to produce an earthquake. It's just not gonna work that way. So there's 2 words that we use. Epicenter is the most common, but be aware that that is that point on top of the hypocenter or focus. Hypo means underneath, like a hypodermic needle, a needle to inject medication under your skin. And so I really like the terminology hypocenter, epicenter, because I like those prefixes, but maybe more commonly that hypocenter is called the focus. And so I might go back and forth a little bit on that. So here's the thing though. Let's say you're in an earthquake that lasts a minute, which would be a pretty long earthquake. It's not that the Earth's blocks here are grinding against each other for a minute. That's not really the way that works. The way earthquakes work is according to something called elastic rebound. And what you need to understand is that rock really can behave kind of like a flexible stick in this case, in that it will bend. And we're going to do a whole thing about structure where we talk about rock bending, okay? And even within the context of earthquakes, there is, what we call an elastic phase here. And so if we think about maybe a transform boundary and what we will later on learn is called a strike slip fault when we do talk about structure. So we've got a block getting pushed this way, and maybe this picture will be better, a block getting pushed this way, and then relatively speaking, this block is getting shoved this way. This is something like the San Andreas Fault out in California. Now, initially what will happen is that rock will deform plastically. In other words, it will bend, okay? Just like a stick held between two hands. If you apply that pressure, it will bend. Eventually, though, that pressure will overcome that rock's ability to bend, and then it breaks and it slips. But it breaks and slips quickly, right? Just like this stick. When this stick breaks, it breaks all at once, right? And so it breaks all at once and it shifts. But then there are waves that are created by that shifting that move outward from that hypocenter, and that's what we feel when we feel an earthquake. We're not feeling the earth grinding along. You're feeling waves that are generated as a result of this breaking and slipping. And then it comes back into equilibrium, as you can see down here, and we're good, right? But right when that stick breaks, you're going to feel all this vibration in your hands, right? That's not, the stick grinding along or something like that, okay? That's the stick bouncing back and forth from breaking. The earth does the same thing. You get that breakage and that brittle deformation, and then it kind of bounces along and resonates and sends out all of these waves. And so that's what's going on. So don't think that, if an earthquake lasts a minute, that's the earth grinding along for a minute. It's not. Right? Those are the waves from that breaking lasting for a minute. It's kind of like, imagine throwing a rock into a lake, right? The rock hits the water and sinks quickly, but the waves from that event can last for however long they last. That's what we're dealing with when we're dealing with earthquakes. So what we'd like to do is we'd like to be able to measure these earthquake waves. And the study of earthquakes is called seismology. It is a very active field within the field of geology. And the machine that we use to measure earthquakes is called a seismograph. Now, I'm going to cop to something here. The machine is called a seismograph. The little readout from a seismograph, I got that. Yeah, here we go. See, I'm already confused. Now, the machine is called a seismograph. The readout from a seismograph is called a seismogram. Now, that is just the opposite of the way I feel like it should be, right? To me, this looks like a graph of the earthquake and should therefore be called a seismograph. But it's not. It's a seismogram. The machine is a seismograph. See, I have to look at the PowerPoint. It's weird. Is it in my head wrong? I don't know. So bear with me here, guys. So anyway, okay, so how does this work? Well, okay, first of all, we don't literally have stands and wires and pivots and rotating drums and things like that. But if you were trapped on a desert island and you needed to build a seismograph from coconuts and boat parts, this is kind of what it would look like. Okay, so what you want to do is bolt the whole thing to the bedrock, attach it very firmly to the bedrock. Then, one way or another, either from a wire or in a pivot or whatever, hang a weighted pin so that the pin is barely right there writing on this rotating drum piece of paper, right? And so what happens now is when the earthquake happens and that bedrock gets shifted around, because that pin is weighted, it's just going to stay in one place on that drum. And that drum is going to move back and forth because it is attached to the bedrock. And so what you will end up doing is quite literally drawing the shaking on that piece of paper. Okay. Now, this, like I said, if you needed to build a seismograph from coconuts and boat parts, this is kind of what it would look like. They don't look like this anymore, right? We don't literally have to like bury them and glue them to things like that. There are seismographs that you can literally drop down a hole. Okay, and they will record earthquakes, and then they will automatically send the signal and the data from that earthquake back to a seismic center, and where it can be recorded digitally, not necessarily literally written on a piece of paper. Okay, here's what these seismic stations look like in the field now. You can see here that you've got a solar panel for power, and then there's a hole there, and at the bottom of that hole is a seismograph, and then they've got this one in a fence because this honestly looks like it's out in a cattle field. They probably don't want the cows bumping the seismograph, but anyway, and there are remarkably portable units now for measuring earthquakes, or seismic waves of all kinds. It's not just earthquakes. We use seismographs to monitor nuclear testing and just all kinds of things. And so there are remarkably portable units now where you can, I was serious, literally drop a seismograph down a borehole and measure earthquakes with it. It really is some amazing technology. Some of this is really remote. Here's a station out in Alaska being serviced by a geologist who needed to take a helicopter to get there. And so, and then here's just kind of a diagram showing, kind of the setup of one of these seismic arrays with these radios and GPS receivers and whatnot to send signal back to the Geological Survey or whatever seismic monitoring agency is using this. So we, like I said, we don't literally have arms and pins and rotating bits of paper. Here's just a picture of what one of these antenna arrays actually looks like, sending data back to seismic monitoring centers everywhere. And so it's a very, very active field. Very active. There's a lot of people working in seismology for a lot of different reasons. We can also, by the way, use earthquake waves to find petroleum. 3D seismic tomography is a whole thing. We use seismic waves for all kinds of things. And if there's not a natural earthquake, we're not above banging on the ground really hard to make one so that we can see what's going on down there. So there's a lot of applications to seismic technology that are not earthquake related, but we're talking about earthquakes today. And so what about these waves? That rock slips and gives and makes waves, and it does. There are a couple of different kinds of waves that we can think about here, and the ones that actually do the most damage usually are surface waves. And I've got some snazzy animations to show you here in a moment about showing these different kinds of waves, but we can broadly divide earthquake waves up into two categories: surface waves and body waves. Surface waves travel along the, oddly enough, surface of the Earth. Body waves travel through the Earth. We are probably more concerned with body waves today. If you are an emergency manager or an engineer, you are probably more concerned with surface waves. We're not going to worry too much about them, but there are two kinds. Love waves and Raleigh waves. Love waves. And I want to make sure let me make sure I get this right. I'm pretty sure I do. And so, love waves move the rock on the surface up and down. And hold on one second. Let me just make sure I get this right so that I'm not messing with y'all here. Love waves move. No, see, I got that wrong. Okay, let's go back. Love waves move it back and forth. Okay, so. Here we are. You got a preview of my PowerPoint, but that's okay. Raleigh waves, okay, move the surface rock up and down. Technically, the rock is moving in a circle. The wave is moving this way, and it literally makes waves on the surface of the earth. Obviously, buildings are not going to do well with this. Love waves, on the other hand, move the rock back and forth on the surface. Okay. And so, obviously, buildings, once again, not going to do very well. So, if you're an engineer engineering for earthquake resiliency in your buildings, these are the things you're going to have to deal with. Now, we might be a little bit more, as geologists, usually, we are a little bit more interested in body waves. Body waves travel through the earth. And they can tell us a lot about the Earth's interior, as we're going to see. And so there are two kinds, and I've got pictures here, and then I've got animations in a moment, as you've seen. But we've got two kinds, P waves and S waves. So P waves are compression waves, and back in the bad old days, before we had animations, we used to use slinkies to demonstrate this, and it works really well. A slinky will actually work well for both P waves and S waves. If I imagine a slinky pulled out and extended a bit so that it'll be more or less straight, and then I take my hand and I push it. Right, I compress that slinky. Well, what happens then is that compression travels down the slinky, right, and then it might even come back, right. That is so now the particles are moving along the direction that the wave is moving. This is a P wave. This is a compression wave. Okay, compression waves. Can travel, they travel faster than S waves, as we'll see here in a minute. So P waves travel faster than S waves. The other thing is P waves can travel through solid or liquid rock. They just can't. And so yeah, so these are P waves, also known as compression waves. Now, now once again, I could use my slinky here too, right? If I take my slinky now, and rather than push it, if I shake it up and down, that makes an S wave. Now the picture I have is a rope. Rope will work fine. So I got a rope. If I shake it up and down, I make this wave that travels down the rope, where now the particles aren't moving along the direction the wave is moving. The particles are moving up and down. They're moving at right angles to the direction of motion, right? And so these are S waves. S waves, they're shear waves, hence the word S. They travel slower than P waves, almost twice, just over half the speed of P waves. And S waves cannot travel through liquid rock. So if there's some liquid rock between you and that earthquake, you're going to get P waves, but you're not going to get S waves. And we'll talk about that here in a moment. So here's my animations. These are better. So there is one P wave at a time traveling down a block, right? And so if it's a slinky, you can think of pushing it. If it's a block of rock, imagine smacking it with a hammer on that end. That's going to make a P wave that travels. And this, the direction of the particles or the rock is, back and forth, the same direction that the wave is moving. Okay, these travel by compression. They travel through solid or liquid, and they're faster than S waves. Here are S waves, right? Now I'm taking my block of rock, and this gets a little harder to visualize, but I'm moving it up and down, right? And so now the direction of wave motion is this way. The direction of the particle motion within the wave is at 90 degrees. It's up and down, right? So these travel by shearing rock. They can only travel through solid rock, and they travel slower than P waves. P waves, I think on average, it depends on the rock and other things, but P waves travel about 1.7 times faster than S waves do generally. And so let's not forget our surface waves. And if I got this wrong before, I think I corrected myself properly, but this is right. So love waves move the rock back and forth. Okay, I know it kind of looks up and down, but look at the end. It's back and forth. Okay, and then Raleigh waves move the rock up and down in a circle within the wave, but up and down. Okay, and so once again, if you're an engineer and you're engineering for earthquake resiliency in your buildings, these are the forces you're going to have to engineer for. Now, I mentioned that that P waves travel through solid or liquid rock, and S waves travel through S waves travel. Let me say it again. P waves will travel through solid or liquid rock, and S waves will not travel through liquid rock. Okay, this gives us a very handy way to study the interior of the Earth. And I'm going to hit pause and come back with something I'd like to show you. So I'll be right back. Okay, so we can use these P waves and S waves to study the interior of the Earth. Let's take a look how. Here's the interior of the Earth, and hold on, I'm going to pause this one more. No, I'm not. So here's the interior of the Earth, and so, we can see that we've got a crust, we've got the mantle, we've got the outer core that is liquid, we've got the inner core that's solid, and we all know this, and you could divide the upper mantle and lithosphere and all that stuff, but we got these layers. How do we know this? How do we know this stuff, right? Maybe we've drilled it. Maybe we've drilled it, right? Maybe we have, right? So let's take a look. Well, this is the colon number 6 super deep borehole. Doesn't look like much, does it? That is the deepest hole on the planet. It is about 40,000 feet deep. It was a project in Russia, and here's what the drill bit looked like. You can see this rock cake to it that looks very, very olivine rich, which is kind of what you would expect down there. Here's what the facility looked like when it was actually operating, and so. This is up in northern Russia, by the way, and yeah. So let's go back to our diagram of the Earth, and let's drill it. Okay, so we've drilled it, right? That's the moral here is that we've drilled. Yeah, no, we haven't. No, we haven't. Let's let's add the Kola super deep borehole to this diagram. See my little red line right there? That's it. That is as far as we have drilled, and honestly, my red line is too thick, too long. Okay, so we haven't drilled it, right? So how do we know what's down there? Now, don't get me wrong. Scientific drilling is good. We learn a lot from drilling. I worked on drilling ships. I've worked on scientific drilling rigs. Never oil rigs. We were always pulling core, but it's good. It's useful, but it's not useful for studying the deep interior for various technical reasons. Drill string, once it gets that long, it starts to chatter around in that hole. It starts to knot up. Bad things happen when you drill thousands and thousands and thousands of feet. It just doesn't work. And so, how do we know? Well, let's say rather than drill there, let's have an earthquake there, right? And so now earthquake waves are going to travel, body waves are going to travel through the Earth. They travel in this kind of a curved path because they are refracted by the increase in density of the rock as you go down. And so they travel in this kind of a curved path. And here's two ways, right? Now notice Right. Let's also be clear. They don't travel in this sort of discrete path here, right? That's not what's going on here, right? They're traveling all throughout here, but I've traced two paths. Well, this path passes through the solid mantle. This is how we know the mantle is solid, by the way, because a seismic station over here is going to pick up both P and S waves, right? But look what happened here. This outer core, this liquid outer core, this path nipped it, right? And those S waves will not travel through that liquid rock. So what do you get over here? All you get are P waves. You do not get any S waves. Okay, now it's actually a little bit more complicated than that. I'm not going to hold y'all responsible for all of this, but it's even more complicated than this, if you can believe it. But if I have an earthquake up here, waves travel through, and all along in here, I'm going to get P waves and I'm going to get S waves. Okay, now what I didn't show you on that other diagram is there is actually what's called a seismic shadow zone here, because what happens is when these waves pass into the outer core, they are refracted even harder because of that massive change in density there, and so they actually end up moving this way. And so even that wave that just barely would nip that outer core is refracted right into it. And so it ends up getting refracted again here, and it comes out over here. So there's actually a shadow zone here between 105 and 140 degrees from that earthquake, where we don't get anything at all, because everything is just these P waves are just hammered deeper into that outer core. Then over here on the other side of the core complex, you get only P waves, right? Because this path traveled through that liquid outer core, and that's going to absorb those S waves, and you'll only get P waves. And so, you do this with enough different earthquakes in enough different places, and there are literally hundreds of earthquakes a day, and so you can do a lot of really good work sorting out what's going on down there. And like I said, it's even more complicated than this. When these things refract, there are secondary P waves and secondary S waves. There's just, the earth just rings like a bell whenever there's an earthquake. And so but seismologists, they live for this stuff. They're down there sorting all this stuff out. Down where, I don't know, but they're digging into these data and sorting all this stuff out and doing lots of really good, really interesting work with this. I'll show you another example of using seismic waves here in a little bit. But yeah, in fact, let me show you a really cool one now. This is the Mars Insight lander. This is a robot currently on Mars. It's got a couple of solar panels for power, and it has two main instruments. One of them is a heat sensor here. So it's pounded this thing down, I don't know how far, to study heat flow up out of Mars. The other instrument, though, over here is a seismograph. It's under a dome because it is so sensitive that wind on Mars, and Mars has a little bit of wind. Mars's atmosphere is about 1% the thickness of ours, so it's not like they're but even that much wind would disturb this thing. It is that sensitive. And so between the heat flow from the interior and studying the seismic waves, we're learning a lot about the interior of Mars. And so this is how we study the interior of a planet, is by studying seismic waves and how seismic waves behave as they travel through it. At least a rocky planet. This isn't going to do you much good on Jupiter or something like that. I mentioned it's complicated. It's complicated. It's very complicated. I don't want to spend too much time on this, but it's complicated. But seismologists, this is what they live for. They just dig into this and can learn a lot. Can learn an awful lot from it. I mentioned one other a little bit more specific application of this. It's kind of interesting. The boundary between the crust and the mantle is called the Mohorovicic discontinuity. MOHO for short, because who wants to say Mohorovicic discontinuity all the time? But the MOHO is this boundary as I said, between the crust and the upper mantle. And it was discovered by a Croatian seismologist named Andraja Mohorovic. And what happened was he was really, once again, digging into these data and found a change in seismic velocities across a boundary here. And he kind of figured out that, wait a second, that's a density change in the rock, and I'll just bet that we're going from crust to mantle across that change. And so that boundary, seismically defined between the crust and the mantle, is named after Andraja. I really doubt I'm pronouncing this man's name correctly. Andraja Mohorovic, and it was defined, once again, it was defined seismically. And so there's a lot of really interesting applications to this this kind of work if you want to go into this. And the green, if I haven't been clear, the green line right here is the Moho, and it actually dips downward here, right at the plate boundary, as the crust goes down. And so it's a really fascinating thing. So let's think about this though. So let's say that I walk into the classroom and I say, hey, there was an earthquake. And you say, okay, where? Well, that's a good question. So how do we locate the epicenters or the hypocenters of an earthquake? Well, okay, so here we go. So you have I'm going to get this wrong, right? You have a seismograph, okay, and it's going to record earthquake waves. Now, P waves travel faster, so P waves are the first to get to your seismic station. Maybe if I just say seismic station, that'll solve my problem. P waves are the first to get to your seismic station, right? So when you look at a seismogram, the first squiggly lines that you see are P waves, okay? The second squiggly lines that you see here are S waves, okay? So P waves travel faster, so they arrive first. S waves travel slower, they arrive second. And so this distance in between them on your seismogram is time, right? And and an interval of distance here, this is, they show you here, this is 1 minute, right? And so 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, right? So in this case, there's a 5-minute lag between the arrival of your first P wave and the arrival of your first S wave. Okay, now, here's the trick, right? The further you are from that epicenter, the greater that lag time is going to be, right? If I have two things and one is traveling faster than the other, then the further I am from where they start, okay, the further apart they are, right? If I have two cars and one's traveling twice as fast as the other, right? Well, 1 mile from where they start, they're going to be so far apart. 5 miles from where they start, they're going to be even further apart. And then 10 miles, you get the idea, right? The further you are from where they start, the further apart they are, right? And so we can see that here, right? You have an earthquake here, there's the hypocenter. P waves and S waves travel, they reach the seismogram first. P waves hit first, S waves hit second. Here, bigger version. There we go. So here at the seismogram closest to the hypocenter, P waves hit, S waves hit, surface waves hit last. Okay, that's the way that works. As you move further away, and they give locations here, I'm not overly worried about those, right? As you move further away, the distance between those P waves and S waves gets to be greater. Okay, and by the time you're down here, even further away, the distance is even greater, right? And so sorry, didn't mean to do that. And so the closer, it's a very simple relationship. The closer you are to the earthquake, the closer together the P waves and S waves are, right? And so here, this is, 1 minute, 2 minutes, 3 minutes, 4, about 5 minutes, right? Here further away, so we get 1 minute, 2 minutes, 3, 4, 5, 6, 7 minutes, right? Here, it's, I don't know, maybe 10 or so, okay? So, or 11 or whatever, doesn't matter. It's further, okay? So anyway, so it's once again, I'm going to say it again, it's a very simple relationship. The closer you are to the earthquake, the closer together the P and S waves are, right? There's a couple different ways to look at this. We could look at a travel time curve showing here how P waves travel faster and S waves travel slower. And so the time difference in between here, you can see distance from the epicenter, right? As you get further from the epicenter, this travel time gets greater and greater, or this travel time difference rather gets greater and greater. Here, it's not very much at all. Here, it's a lot. There's an easier way to graph this though, right? And it looks like this. And so, the lag time in seconds, S minus P, right? How many seconds difference is there between the first P wave and the first S wave? And distance, right? And what we can see is the case that I talked about before, where the closer you are to that epicenter, the less that time lag is, right? The fewer seconds that time lag is. So how do we use this? Right. Well, so we know how, from a single seismic station, looking at the P wave, S wave lag, and let me just go back here. We could tell how far away the earthquake is, right? If we knew how many seconds the travel time lag was. Let's say that the travel lag was 50 seconds. So let's say there were 50 seconds between my first P wave and my first S wave. I can come over this line. I can come down, and I am just under 500 kilometers from the epicenter. Awesome. But that's not where it is, right? If you ask me where something is and I say it's about 50 miles away, okay, but that's a circle. That's not a location. So how do we do this? Well, here's what we're going to do. So what you need is 3 seismic stations. Now, bear with my lousy little seismogram drawings here, okay? But yeah, just bear with me. So at seismic station 1, here's the first P wave, here's the first S wave, and there's going to be a time lag in between them that we can measure. It doesn't matter what it is, but we'll get there. So anyway, so first P wave, first S wave, measure that time. We call that time delta T. The Greek symbol delta, don't freak out. It just means the difference, right? Whenever you see delta something, that means the difference in something. And so in this case, it's the difference between the P wave arrival and the S wave arrival. Okay, so there's that. And so now we have another seismic station. There it is, right? P waves and S waves are closer together. This one is closer to the epicenter. Okay, first P wave here, first S wave here, delta T there. Okay, whatever that time lag is, specific numbers aren't really important. Okay, third one. Okay, right now we're really close, right? Delta T is very small. You can see that the waves get bigger as you get closer. I was thoughtful enough to do that, but this shorter distance here means that that station number 3 is closer to the epicenter. Okay, now let me go back. And remind you of this graph right here, right? This graph will allow us to turn time lag, or this axis is delta T, into distance, right? I did it before, right? If my delta T is 60 seconds, if I follow this line over to my diagonal line and then come straight down, I can read off about 580 kilometers in this case, okay? So we can do that. So if I go back here, put my size graphs back up. Now, I just kind of reproduce that drawing without without numbers on it, okay, qualitatively, right? Just to show you what you can do, right? And so what you'll do then is take that delta T, find it on the graph. I know there's no numbers on it. Pretend there's numbers on it, right? Find it on the graph, come over come down, read off that distance, right? So you'll have an actual numerical distance. Do the same thing for the second seismogram. See, I almost did it again. Come over, come down, read off that distance. Third one, over, down, read off that distance. So now I have 3 distances, right? So now what I did was I used my travel time difference to actually get a distance. Okay, and so now what do I do with those? Well, I pull out a map, right? I pull out a map, and my map has where my 3 seismic stations are physically located, right? Then I draw a circle around the seismic station with a diameter of the distance that seismic station is from the epicenter, right? And so for my green earthquake here, seismic station 1, I get a number that's fairly big, and so I, use the scale on the map, draw a circle, right? So I know that my epicenter is somewhere around that circle. Take the second seismic station, do the same thing on a map. It's here, there's that thing, draw that circle. So if it's this far from seismic station 1 and that far from seismic station 2, it is either there or there. Okay, I'm giving it away, but you get the idea. And so do the third one, maybe it's sitting right here, draw that circle. All 3 of those circles cross at the same place, bingo, there's the epicenter. If you want to know the hypocenter, you do it in 3 dimensions, and you need at least 4 seismic stations. I can barely draw 2, so let's not worry about that, right? And so, yeah, now, you need at least 3. In reality, you have hundreds. You have hundreds of seismic stations, especially in earthquake-prone areas. Once you know what to look for, they're all over California. You can't miss them, right? You don't need to be that close. You can be pretty far away. This one is 8,200 kilometers from Paris and 4,900 kilometers from Darwin and 3,400 kilometers from India, Nagpur, I guess is how you pronounce that. And sure enough, there's the epicenter there, where all 3 of those circles cross, right? And so that's how we figure out where the earthquake is. I'm going to move on to measuring size, but I'm going to take a quick break and check on a couple things. I will be right back. Okay, I'm back. I'm not going to put a little 5-minute break in here because I don't have that much to go. And so, but you should obviously feel free to take a break and walk around and whatnot if you need to. Just hit the pause button. I had a sneaking suspicion I wasn't recording. The good news is I was. So hooray. So anyway, so once we know where the earthquake is, our next question is how big is it? And there's a couple different ways to measure how big an earthquake is. One of them is the intensity of the earthquake, and we measure this using something called the Mercalli scale or the modified Mercalli scale. You probably never heard of this. No one outside of the science of the field has, but we do use it, and I'll show you how in just a moment. But Mercalli is basically how much shaking there was. Now, the thing about Mercalli is, as you move closer to the epicenter, the Mercalli number is going to go up. As you move further away, the Mercalli number is going to go down. It is a sort of qualitative scale. You can see here that, a Mercalli 5 is felt by nearly everyone, many awaken, disturbances, etc. A 6 is felt by all. A 7, everybody runs outdoors. So in a silly kind of way, the Mercalli number depends on how many people are running around screaming, right? It also, though, has to do with damage. Damage negligible in buildings of good design, damage slight in specially designed structures, but considerable in ordinary structures. The problem with Mercalli is it relies on people's perceptions and people's kind of qualitative observations. You could have 2 equally qualified people sitting on a damaged wall arguing about the Mercalli number because they disagree about how well built it was or how bad the damage is and whatnot. So, it is useful though. You don't need to be around for the earthquake, right? You can dig up an ancient Mayan temple or something with earthquake damage and give it a Mercalli number. And people who do this kind of work are better than I have made it out to be. The other thing you can do, though, and I'll show you this here in a few minutes, is you can poll people, right? And in the internet age, you can say, hey, did you feel that earthquake? Fill out this survey. Let us know what you think, and we're going to make a map of the Mercalli number for that earthquake, and I will show you that here in just a second. But this is sort of qualitative, not sort of, it is qualitative, right? You know, two equally qualified experts could sit on a wall and argue about it. Okay, so we do need something quantitative. And so rather than measuring the intensity of the earthquake, we're going to measure the magnitude of the earthquake. This is the amount of energy that the earthquake released, commonly known as the Richter scale. But I'm going to give you the little inside scoop here. We don't actually use the Richter scale anymore. We use something called the moment magnitude scale. It is essentially the same thing. The math is just a little bit different. Now, the thing about the moment magnitude scale is it doesn't matter how far you are from the earthquake, right? The earthquake releases the same amount of energy no matter where you are, right? We're not measuring damage or intensity of shaking or something like that, right? We're measuring how much energy it released. So it is quantitative. Okay, so by that what I mean is we got a formula, right? There it is. It's not that bad, but it's a pain. But there it is. Okay, and I'll talk about that here in just a second. So so this the Richter scale, or the moment magnitude scale, I should say, doesn't have a top or bottom, but it's calibrated in such a way that you're going to get a number between 1 and 10, or I should say 1 and 9 point something. Okay, and I'll talk about this more here in a moment. But every whole number you go up represents 30 times more energy released by that earthquake, right? So the reason for that is because the formula involves logarithms, and logarithms. Remember, ask yourself what exponent do I use with a 10 to give me that number? Okay, so not to give you weird algebra flashbacks, but you need to know two things. You need to know the amplitude of the largest S wave, and you need to know delta t, which is the travel time difference, right? Plug into that formula, and it spits out a number between 1 and 10 that represents the amount of energy released by the earthquake. Now, this formula is not that bad. I mean, you can do it. It's not that big a deal. But a lot of times when we deal with moment magnitude or magnitude scales in general, we'll use something called a nomogram. A nomogram is a graphic way to perform a calculation. And in the era before we all had little supercomputers in our pockets, these are very common. A lot of my professors at Florida State and Texas A&M had these books of nomograms for doing all kinds of calculations. And so what you do here is you take your seismic record, and you literally slap a ruler down on it, and you measure the amplitude of the largest S wave in millimeters. It's the weirdest thing. You just literally slap a ruler down on there and measure it in millimeters. Then you measure the time offset between the first P wave and the first S wave. And then what you do is you place a straight edge along your nomogram. Put one end of your straight edge at the amplitude, put the other end of the straight edge at either the SP interval, 24 seconds, or if you convert it to distance, you can do that. That's fine. And then what will happen is, magically, because of the way the nomogram is calibrated, it will cross this line at the magnitude. And so you can see how if the amplitude goes up and your straight edge is more up here, the Richter magnitude gets higher. If the amplitude goes down, your Richter magnitude is lower, right? If you're getting the same amplitude further from the earthquake, that means the magnitude is greater. If you're getting the same amplitude closer to the you see how this works, right? As you move around on this scale, as you move around on that scale, where you cross that line changes, and that's the amplitude, right? And so basically this formula is built into this nomogram, and it's a good way to calculate this. But so let's think about this though. So I whipped up a little a little, what is that, a table, kind of um, showing the amount of energy released. So the trick here is every whole number you go up on the moment magnitude scale releases 30 times more energy. So, okay, so look, no one cares about a 1, a 2, or a 3. Okay, you're barely going to feel a 3. Okay, a 4 is when, the building around you is shaking and just about everyone can feel it. Okay, so let's set that sort of qualitatively, right, to 1. Okay, now a magnitude 5. So here things are going to shake. There's not going to be any damage. No one's going to die. Nothing like that. Right? It's going to shake. I was actually in one of these a couple months ago. I felt it. My mom didn't. It's just the house just shook a bit. Okay, and I'm in North Carolina. It was crazy. But anyway, okay. So a magnitude 5 releases 30 times more energy than that 4. That's a lot more energy, right? And so now, yeah, you're going to get some damage to the buildings. You're going to want to check your highway overpasses for cracks. Your chimney, brick structures, things like that might be cracked. Probably not going to kill anyone, but you're going to do some damage. Now, a magnitude 6 doesn't just release 60. No. 30 times 30, 900 times more energy than that 4. Right? A 6 isn't like 50% worse than a 4. It's 900 times worse than a 4. Now your buildings are definitely going to be damaged. Some of them are going to collapse, and people are going to start dying now. This is a real problem. Okay? By the time you get to a 7, that's 27,000 times more energy than that 4. That's 30 times 30 times 30. Okay? Now buildings are collapsing. Lots of people are dying. A magnitude 7 pretty much leveled Haiti a few years ago. Okay. Now, obviously, how much damage happens depends a lot on building codes, and all kinds of other things. But still, 7s are nothing to play with. The big earthquakes in California are like 7s and 8s. Okay. So these are now it's a problem. Okay, a magnitude 8 is 810,000 times more energy than that 1. Right? It's 30 times 30 times 30 times 30. These numbers go up fast. Now you're leveling cities. Now you're also worrying about tsunamis. Everything from a 6s, you don't worry too much about tsunamis. 6s and below, you don't worry too much about tsunamis. We'll talk about tsunamis here in just a second. 7s, you do. 7 and up, you start worrying about tsunamis. So with 8s, we're leveling entire cities. Lots and lots of people dying. Once again, deaths and damage don't just depend on the magnitude of the earthquake. They depend on your building codes, how educated your populace is, all kinds of things. 9, 24,300,000 times more energy than that 4. So imagine, baseline energy release that shakes your house a bit. 24 million times more energy. Now you're leveling regions. Now we're talking about Japan. And I believe 2011, a few years ago, massive tsunami danger, really, really a problem. And then thankfully a 10 has never happened. We've been up into the 9.6s, 9.7s. I'll show you here in just a moment. Thankfully, there's never been a 10, but if there was, it would be 729 million times more energy than that 4. So you can see that, if you multiply the amount of energy released by 30 for every whole number you go up, you start getting into ridiculous amounts of energy pretty dang quickly. The good news is when you start getting to the top of that scale, you don't get that many. This is sort of the classic drawing that people always show. And the width of the graph here represents the number of earthquakes of this magnitude that you get. And you can see that, if you're down around Two, you're getting, a million of those a year worldwide. No one cares about these. These don't really do anything, right? It's not until you get up in here that you really start getting problems. So they threw some earthquakes on here. Chile in 1960 was way up here at a 9 point something. Alaska 64. There's Japan in 2011 up there above a 9. I mentioned. We'll talk about the New Madrid earthquake here in just 1 second, or earthquakes. But there's Haiti in 2010. See, the funny thing, Haiti got hit with around a magnitude 7 in 2010, and it pretty much leveled the country. Okay, Chile. Notice here, Chile. Also in 2010, just a couple weeks later, a magnitude, I think it looks like it's almost a 9. But Chile was like, you know what, guys? We're fine. Take care of Haiti. Chile is a first world country with a functioning government. Haiti is not. And so, how much damage these earthquakes are going to do definitely depends on the magnitude, but it also depends on how well prepared your populace is and what are your building codes like, and, et cetera, et cetera. So there's a lot that goes into earthquake mitigation. The Japanese are very good at it. Chile's very good at it. We're okay at it. We're not great, but anyway. But this will give you an idea. And then on this side, sorry, I don't have the plague. I have heartburn. So on this side, you can see some other things, right? So there's the energy release of a tornado. There's the atomic bomb dropped on Hiroshima, largest nuclear test. There's a volcanic eruption, Krakatoa, really big volcanic eruption. Here's the Mount St. Helens volcanic eruption. Not in terms of damage, but in terms of just how much energy is being released. And here it is in equivalent tons of TNT, which frankly doesn't mean much to me, but 15 billion seems like a lot. So is that billion? That's billion. Trillion? Really? Million? Yeah, trillion. Wow, that seems like a lot. Anyway, okay. Let's talk about an unusual earthquake, because there's some interesting stuff happened here. So people kind of know about the 1906 San Francisco earthquake. If you don't, Google it. It's kind of interesting. But maybe an earthquake that's a little bit more interesting that a lot of people frankly don't know about happened in New Madrid, Missouri. In 1811 and 1812, and it was a series of earthquakes, 4 major earthquakes, magnitudes in 1811, 1812, Missouri was not exactly thick with seismographs. In fact, I don't even think it had been invented yet. So we're having to estimate the range, but the range of these earthquakes was around 7 to 8 in that area, right? And so, but the problem is there were 4 of them and then several hundred aftershocks. I mean, there were earthquakes happening almost constantly, and some of the aftershocks were 5s and 6s and 7s, and so it was really an extraordinary time. There were, waterfalls formed on the Mississippi River. There were waves as a result of these earthquakes traveling up the Mississippi River, which actually, in one case, washed over and made a new lake that is there to this day. What few buildings were there were absolutely leveled. I don't think there was any loss of life, because it's not like people were living in skyscrapers in New Madrid, Missouri in 1811. But there was a lot of destruction. It was just an amazing event. And so here's the map. And so, Kentucky over here, Tennessee here, Memphis, St. Louis, and so here's the Mississippi River there, and then there's Missouri, Arkansas, and so there's the town of New Madrid, right there. And so and geologists call this the New Madrid seismic zone. As we will see here in a moment. In fact, let me pause this and bring. Actually, let me Yeah, let me pause this and bring up the earthquake browser and show you the New Madrid seismic zone. I will be right back. Okay, back. These earthquakes happened in an area called the New Madrid seismic zone, and you can see here on the map. Here's St. Louis up here, Memphis, etc., Missouri right there. And so I went over to the Iris earthquake browser, and I basically said, show me every earthquake that's ever happened in this area, and you can see there. Now, not all of these are that 1911. There are 1911, 1912 series. There are earthquakes happening here to this day. There are, well, there have been earthquakes here within the last week. So this is not, this is not just the event that we're talking about. This is the New Madrid seismic zone. And so you can see a very, well-defined area here, another one coming up here, another one down there, another one down through here, and so that is the New Madrid seismic zone. And so what the heck? I mean, what's going on here, right? I mean, we understand earthquakes along the San Andreas Fault. We understand earthquakes, in the Pacific Northwest. So what's happening here? Well, what's happening here is an ancient Precambrian failed rift called the Reelfoot Rift. And what happened was, what is today North America tried to break apart there. It failed. It obviously did not, because here we are. And in fact, the Mississippi River is kind of following the path of that Reelfoot Rift. It's about a 750 million year old rift. And so this New Madrid seismic zone is there because of the Reelfoot Rift. And so here's a diagram of it kind of from the side. And you can see we've got some magma bodies here that came up when this was trying to rift. We got some faults. These are normal faults. When we talk about rock deformation, we'll talk about normal versus reverse faults. And so you got a lot of ancient inactive faults down here that would be very easy to activate. And when you combine this weak rock with regional compression, the regional compression of North America that reactivates those faults. See, here's the thing. When I say regional compression, what I mean by that is North America is getting squeezed. We've got the mid-ocean region, the Atlantic, pushing us to the west, and then there's nothing on the west coast of North America to relieve that pressure, right? The west coast of North America is a transform boundary, the San Andreas Fault. That's not going to relieve the pressure of North America getting pushed westward. And so consequently, we get a lot of what we call inboard or intraplate earthquakes here in North America. And what I mean by that is earthquakes that are not associated with a plate boundary. If we get earthquakes, we get a lot of earthquakes far away from plate boundaries. Other countries do not get this, and I could go through the Google or I could go through the Iris browser or get on Google Earth and show you, but I'm not going to. Just take my word for it, or look for yourself. You'll notice there are a lot fewer earthquakes in other continents that are not associated with plate boundaries. We get a lot of earthquakes kicking off right in the middle of our continent, and this series is one of them, or one series of them. If there's any weak rock, and in this case it's the Reelfoot Rift, but if there's any weak rock anywhere in the interior of North America, it's going to break and it's going to slide. If you do go and look on the Iris earthquake browser, you're going to notice a lot of earthquakes in Oklahoma. Those are man-made earthquakes. That is hydraulic fracturing, creating weak rock and earthquakes. There were no earthquakes, or very few earthquakes, in Oklahoma before they started hydraulic fracturing. And so there was a time when if someone had asked me, could people make an earthquake, my answer would have been no. It's not so true anymore. So anyway, let's talk about something else though. Something that happens as a result of earthquakes. On my site, I mentioned that from a 7 and up, you start worrying about tsunamis, and you really do. Tsunamis are these big waves, quote unquote, tidal waves, although they don't have anything to do with the tides. But I think we all know that, right? But if I say the word tidal wave, I think that gets the right image in your mind. There's a number of things that can cause these. Landslides both above and below water can cause kind of local tsunamis. Meteor impact. If you get a meteor landing at sea, that can cause a tsunami. I've worked some of the meteor deposits from the dinosaur extinction, some of the meteor tsunami deposits from the dinosaur extinction in Texas. Definitely an option there. But volcanoes can cause them, but really earthquakes, right? That's really what we're talking about. And what you see here is in 2011, that tsunami in Japan. What you see here is the tsunami flowing over the tsunami protection wall. Okay, Japan gets hit by several tsunamis a year, by the way. You just don't usually hear about it because they are very well prepared for a tsunami. They really are. It's just not really politically or socially feasible to engineer for the magnitude of the tsunami that hit them in 2011. People don't want 50-foot walls around their city. They just don't want to do that. And so the fact that there was so much damage as a result of that tsunami just speaks to how bad it really was. Japan is not at all unprepared for a tsunami, but no one is prepared for a tsunami the magnitude of which hit Japan. Here's speaking of which, here's a map of that tsunami. That's just the offset, the maximum wave amplitude, and so you can see that it's spread all over the Pacific Ocean. 90% of tsunamis happen in the Pacific Ocean. Most of the other 10% happen in the Indian Ocean, as you might remember from 2004, although that's reaching back a bit now. Tsunami in Indonesia killed almost 1 million people, I think 800,000 people all around the Indian Ocean. But most are happening in the Pacific, and there's a reason for that. And that is the tectonic setting that is required, or usually required, to make a tsunami. And that is an ocean-continent convergent plate boundary. Okay, and as you know, the Pacific, I can go back to that previous slide, is surrounded by ocean-continent convergent plate boundary, right? Ocean will do it too, but ocean-continent is more common. So there's ocean-continent boundary there, ocean-continent boundary there, transform there, but up in here, around in here, around, this is all the right place to make a tsunami. And so a lot of these things get kicked off in the Pacific Ocean. But what is so special about this plate boundary that makes tsunamis? Well, here's the trick. It's not the shaking that makes the tsunami. You need a specific kind of motion on the ocean floor to make a tsunami, and it needs to actually breach the ocean floor. So at an ocean-continent convergent plate boundary, you get the oceanic plate going down. This plate, the continental plate, will shorten a bit and wrinkle back, and you might actually even get some uplift here, right? And then when it gives, this wall on top that we call the hanging wall needs to move up into the water. You actually need to displace rock up into the water. It's not the shaking that makes the tsunami, right? Imagine you have an aquarium, right? And you put a plate on the bottom, a metal plate on the bottom of your aquarium, and somehow you're going to just shake that metal plate. Right? That's not going to make a wave. That's going to make just little ripples in the water above, right? It's not going to do that, right? Now take your hand, put it on the bottom of your aquarium, and shove it up. Right? Now you're going to make a wave, okay? And this is an initial condition from a model that I found. I just did a quick screen capture of it. And you can see that what's happening here to make this wave is that seafloor is rupturing and moving up, right? That's what makes the wave, not the shaking. The shaking won't do it. You need a fault to rupture the surface, and it needs to and then it's going to need to rupture the surface, shove a block upward that shoves the water on top of it upward, and bingo, you have a wave. Okay, so here's the thing, right? Let's say that you live in an earthquake prone area. Okay, so it's simple, right? You're an emergency manager and you say, okay, look, I know that, magnitude 7 and above earthquakes can produce tsunamis. I'm going to be safe. I'm going to go down to a 6. So whenever there's a magnitude 6 or greater earthquake, I'm going to yank everyone off the beach. Okay? That will not work. Okay? That will not work. Okay, because people get tired of evacuating, right? Evacuation fatigue is a thing, and you know this, right? About the third time they evacuate us for a hurricane that doesn't hit, that fourth time, you don't bother, right? It's a pain, right? People don't want to be running around getting yanked on and off of the beach every time there's an earthquake. They just don't. Now, me personally, I'm a run. It's just not worth it to me. But from an emergency manager's point of view, you can't just think there might be a tsunami, so I'm going to yank everyone off the beach, because after a while, people will stop paying attention to you. So you need to actually know that there's a wave out there, right? Because not every magnitude 7 or 8 earthquake is going to make a tsunami, right? You need this pretty specific motion, okay? So we need a warning system. Well, these waves that tsunamis make have wavelengths of hundreds of miles, which means that the energy from that wave, the motion of that water, reaches all the way down to the bottom. And so that's the key to a tsunami warning system, right? What you do is you put a pressure transducer all the way on the bottom. The wave goes over, it pops that sensor. That sensor talks to the buoy. The buoy talks to the satellite. The satellite talks to the emergency management center, and they can say, "Oh yeah, there's a wave now. Get off the beach," right? And so this makes a much better way of doing it. Now, before the 2004, before the 2004 tsunami that killed so many people, there was not a warning system in the Indian Ocean. Now there is. Those islands of Indonesia, Java, and Sumatra, that is an ocean continent boundary. And so there is most definitely the potential for tsunamis here. There's also a slight potential for tsunamis in the Caribbean, which is an ocean boundary. Not as much, but some. I was there doing some work a few years ago, and there were most definitely tsunami warning signs around there, showing where to go in the case of an earthquake and a tsunami, and basically uphill. And so yeah, I am going to put a video in my courses. I can't. I would normally just try to show it to you, but it doesn't work. They copyright stuff, and so I can't just do that. But I'm going to put a video in my courses of a tsunami. Of that Japanese tsunami in 2011. And the thing that I like about this video, first of all, you're not going to see anyone die, but the nice thing about this video is it shows you what a tsunami looks like in one place. It is a continuous video taken by one person from dry ground to tsunami. And so this will give you a really good idea about how these things behave and what you're having to deal with when you deal with a tsunami. Meanwhile, let me bring up my web browser up, because I want to talk about this. I want to go back and talk about this this Alaskan earthquake for just a few minutes, and then we will be done. So I'm going to hit pause and do my thing. I'll be right back. Okay, everyone, back with the Iris Earthquake browser in our earthquake swarm area. And so let's, I've got it set to show me 1,000 earthquakes, but only in the last 3 days. So this would be everything that's happened out there up until now. And so let's take a look at this three-dimensional view, because this is something that is I think will be very useful to us. So it's once again it's showing it to us in 3 dimensions, and so you can see we look kind of straight down on it. We can see epicenters, but then also hypocenters where it's underneath the surface. But if we look at this, they're not that deep. They're just not that deep. And so, a magnitude 7 earthquake that shallow, I would really start thinking about tsunamis, especially in this setting, because they're just not that deep. These earthquakes are happening in the overlying crust, right? Remember what's going on here tectonically. Tectonically, you've got the Pacific plate here. Let me back out a little bit. You've got the Pacific plate here getting shoved underneath the North American plate, right? This is a convergent plate boundary, and so as it goes down, you get grinding and you get earthquakes. But a lot of times you get earthquakes. So I keep this, like I said, clunky. A lot of times you get earthquakes not only on that subducting plate, but on that overriding plate too. Right, you don't just get earthquakes along the Wadati-Benioff zone going down. There's a lot of pressure being applied there, and you'll get earthquakes in that overriding plate. And looking at this three-dimensional view, I really get the idea that these earthquakes are happening in that overriding plate. They're not sinking down into the mantle along the Wadati-Benioff zone. If you're in the lab, you did this snazzy little graph where you graphed the earthquakes at a plate boundary. And you saw how some of them are in that overlying crust, but then some of them follow that Wadati-Benioff zone, that subducting plate down into the mantle. That's not happening here. These are all fairly shallow earthquakes. And so let's take a look at the USGS page for this. There's a lot of information on here. We're only really going to talk about some of it. But first of all, it was felt by 309 people who reported it. So there's not too many people living out here, really. But remember the modified Mercalli scale? And how I said we'll come back to this, because one thing you can do is you can poll people to get a Mercalli number. So if you did feel it, you come here and you tell them, right? You fill out a survey. Did you feel it? Let's say we did, right? And then you can go down here. What was your situation? Were you asleep? Did anyone else feel it? How would you describe the shaking? How did you react? How did you respond? Like I said, I was actually in an earthquake up here in North Carolina a couple months ago, and I got to fill one of these out. I was so happy. It was crazy. But anyway, you fill out this survey. In the end, it's like, fences, walls damaged, refrigerators, rocking back and forth. I mean, it's kind of interesting. And then, you fill it out and you hit submit. And then what they're going to do is they're going to use that to make a shake map. Now, the shake map for this particular earthquake doesn't look like much, because it's just not that populated. Let's look at a shake map from the Northridge earthquake back in 1994. So this is an earthquake that happened along the Northridge Fault in California. And so lots more people. And lots more data. And the reason you want a shake map, right? The reason we use this Mercalli scale, right? We got these weird Roman numerals down here, right? As you move closer to the epicenter, the Mercalli number goes up. As you move further, it goes down. But take a look. There's the epicenter right there where the star is, right? The worst of the shaking was actually to the north of the epicenter, up towards Santa Clarita. So if you're an emergency manager and you want to, deploy your people to the area that has the most damage, it's not necessarily, a series of concentric rings around the epicenter, especially in California, where you have very variable geology and lots of stuff going on, right? And so this is what we actually use the Mercalli scale for, is you poll people. Nowadays, you can do it on the internet, and you can make a shake map based on the Mercalli numbers for those for that particular event. And so, in this particular case, it's not really. I mean, it doesn't look like much because there's just not that many people. But if you have a more populated area. It can be a very, very useful thing. So this thing is only 33 kilometers, 20 some odd miles deep. So that's pretty shallow. And it's also pretty big. So you start thinking tsunami at that point, but there wasn't one. Not really. There was a small one, like a 2-foot one or something like that. We'll see that here in a minute. So what happened? Why wasn't there a tsunami? Well, The key to that lies in this moment tensor solution, and I'm not going to teach this in any detail because it's beyond the scope of this class, but we call this a beach ball. And what this does is this tells us, with a two-dimensional drawing of a three-dimensional thing, how the fault moved. And here's the trick. What this tells me is this was what we call a strike-slip fault, kind of like you would call a transform plate boundary, right? These two blocks were sliding past each other, mostly. There was a little bit of upward motion, but mostly they were sliding past each other. That is generally not going to make an earthquake, right? What you need is a fault where one block gets tossed upward into the water. Now that happened a little bit here. If we were looking dead straight down on that X, that cross right there, that would be purely moving past each other with no upward or downward motion at all. Okay, in this case it's offset a little bit. That tells me that it was mostly sliding past, but a little bit of upward motion. So for a magnitude 7, once you know this moment tensor solution, you might not expect such a large earthquake. If we get more earthquakes, I might try to find you a different moment tensor solution so you kind of know what what one looks like where you might get a tsunami. But it turns out there was a small tsunami, which you would expect. I mean, it's not dead on past each other. There was a little bit of upward motion to that fault, and at only 33 kilometers down, it probably breached the surface a little bit. Okay, but yeah, if we look at I sent this out in an email, this Washington Post article about the earthquake, and I was kind of reading it, and it was kind of the usual, and then something really caught my eye. So this guy, David Adams, who was in the earthquake, he said, look at what he said. He said, you could see the water kind of shaking and shimmering during the earthquake, right? That's what you expect. Right? I mean, imagine, go back to my metal vibrating plate on the bottom of your aquarium, right? That's not coherent motion enough to make a wave like a tsunami, but it will make the water kind of shake and shimmer and whatnot, right? It's not going to make a wave, but it will disturb it. Right? And so that's mostly what you would expect from this. That really struck me. I was like, there we go, right? There was a small tsunami. I mean, seriously, 2 feet, right? Which is not that big a deal. But there was a small one. And that makes sense given that moment tensor solution, right? This is not purely back and forth motion. There is a little bit of an upward component. Trust me, if you really want to learn moment tensor solutions, I can teach them to you. But they require a three-dimensional visualization that is really sometimes gives me a headache. So anyway, big earthquake, shallow focus in the crust, right? Which also, by the way, explains why you didn't get rock displaced upward into the water, right? That wasn't happening along that subducting crust where you might expect that to happen. Once we talk about rock deformation, I'm going to come back to this because we'll have better vocabulary at that point for talking about this. For now, I'm kind of having to talk around some terms that we're going to learn when we talk about the deformation of rock. So anyway, fascinating earthquake, interesting things going on there. Nothing unexpected. Mostly what we call a strike slip or what you would call a transform fault earthquake. Not going to make a tsunami, but a little bit of upward motion. So you got a little bit of tsunami. It all kind of holds together very well, and it all kind of makes sense. So like I said, when we get to rock deformation, I'll have some better words to use with you guys. But for now, I think that will do it. So thank you all very much, and we'll get this uploaded. Okay, bye-bye.